Yeah, good evening, everyone. Yeah, I see so much excitement in the faces of almost everyone here. It tells me that everyone is ready for today's talk. We've been looking forward to it, working towards it over the past couple of weeks. All right, so you're welcome to the ALMET Yorkshire talk for today. We have Dr. Caroline Baine here with us, and then she's going to talk to us on the challenges of weather forecasting in Africa. Yeah, there's so much to learn from Dr. Caroline Baine, because she's a numerical weather prediction expert with a specialist knowledge of tropical weather and climates. And in academia, she's also based in University of Reading, Imperial College, and the University of Leeds, and then moved to University of California. At the Met Office, she has held both research and leadership positions in science, international development, and now in technology. She has led teams of scientists who develop, use, and evaluate weather forecasting models in Africa and Southeast Asia. She has a strong commitment to the uplift of national meteorological services in developing countries, and is passionate about ensuring the benefits of NWP are shared among the global meteorological community. So in the next about 15 minutes, I'm going to hand over to Dr. Caroline Baine to talk to us on the challenges of weather forecasting in Africa. So shall we welcome Dr. Caroline Baine?
Thank you. If people can't hear on the video at any point, just shout, because I can't see what's happening on Zoom at the moment. But first of all, thank you very much for that warm welcome, and it's a real pleasure to be here in person. So this is really exciting for me as well. And if we don't get through all the questions at the end, just feel free to call me, or if you want to email me anytime, my contact details at Met Office are just caroline.baine@metoffice.gov.uk. So if you think tomorrow or the day after, oh, actually, I wish I'd asked that, just email me anytime. So I thought, I didn't know who was going to turn up, and it's quite intimidating giving a talk about African forecasting at Leeds, because there are so many people here that at the university faculty who know about African forecasting and might even been African forecasters as well, including Michael, who's just introduced me. He was a forecaster in Ghana. So I felt a little bit like I didn't want to sort of pitch it too high or too low. So I think this was kind of a bit of a first slide, just to say that maybe keep in your head about what you think might be the main challenges of weather forecasting in Africa. And if you have like a pen or anything like that, write it down, or like just think about it. And then we'll bring it, hopefully we'll go through the whole talk. And if I've answered your question, or if I brought up something that you thought would be the issue, then that's great. And if not, then please raise it, because I'm quite happy to be challenged at the end as well. Okay, so yeah, my name is Dr. Caroline Baine. I'm from the Met Office. I'm no longer really working in African weather, apart from with my PhD students here at Leeds, which is obviously a pleasure. But I work mainly in the UK now, so I do a lot of tropical and UK work. But I have to say, Africa is my first love. So my real passion for meteorology started during my PhD almost 20 years ago now, when I started studying African meteorology. Oh, yeah, sorry, you can see the storms there. I also wanted to first up put a pretty clear acknowledgement that this talk is dedicated to the National Meteorological Services in Africa. I'm a super fan, but I'm not an African forecaster. So all of the things I cover here are kind of my impression from the outside looking in, but there's a lot of really committed staff at the National Met Services in Africa who, hard work and dedication, especially provides observations for the World Meteorological Organization, so the World Monitoring Network that we have, and they share those observations free of charge with all the other national Met services in the world, and that helps not just their countries, but also even the UK as well. So we rely on all national Met services worldwide to share observations, and this is something that is really one of the most kind of generous things that we do. And in fact, the WMO is one of the kind of longest serving and most friendly UN agencies, if you like, in the world. I'm really proud that the Met Office and that we're part of this kind of really high functioning agency where there's a lot of kind of sort of free sharing of observations across the world. So I thought it was worth kind of starting with the question of like, what type of weather do you think of when you think of Africa? And I guess that a lot of people, you know, if you don't know anything about Africa, or if you just sort of watch the telly and you just looked at television news, you just think of deserts and kind of dry and lots of drought. But actually African weather can be more complicated than that. You can have floods as well. This photograph was taken in Hombori in 2005. This was a large, the claim to fame is that I was standing here, I took a photo in 2005, and this was a storm that then went on with the mesoscale convective system. The whole system started rotating when it hit Senegal, went into the Atlantic, and it formed a small tropical cyclone, which then went on to become a bigger tropical cyclone, which went into Hurricane Katrina and hit the US in 2005. So this was the beginning of Hurricane Katrina. There's nobody, you know, there's not very many people who've got a photograph of this, like 10 days before Hurricane Katrina formed. But you might not know, you also get snow in Africa, and there's even a ski field in Lesotho as well in southern Africa. So snow can be a problem in very few countries, but one or two. And then this photo is taken from Kenya. So Kenya suffers a lot from fog, as do a lot of the kind of high areas in East Africa. But today I'm going to talk mainly about convection. So these are kind of large thunderstorms, and this is quite typical of Sub-Saharan Africa. So this sort of covers the main region from the sort of Sahara Desert all the way down to South Africa. So what is convection? Convection, in other words, thunderstorms, is very prevalent in the tropics, and in the tropics, convection matters. They can be influenced by sea surface temperatures, as well as large-scale synoptic pressure gradients. But the strength of the influence is different for each country, and so it's very difficult to say a general rule of thumb. So what I'm going to do now is take you through the kind of basics of how convection moves around with the seasons in Africa. Oh, before that, sorry, this was actually a plot that is a bit of an ugly plot, but I did it because I wanted to show that actually convection is so important that there are parts of Africa that get the majority of their rainfall from heavy rainfall days. So this is a June, July, August, September sum of rainfall where the day has, the location has received above 20 millimeters per day. So 20 millimeters is a really, really strong rainfall event. And that's saying how much rainfall do they get from events that occur that are 20 millimeters a day. And this is how much rainfall they get from rainfall that's under 20 millimeters a day. So in other words, there's a light rainfall event. And this is the heavy rainfall total minus the light rainfall total. So what this is saying, if you take nothing else, is that in the blue areas, they get the majority of their rainfall for the whole year from very, very heavy thunderstorms. And that's really, really significant, because what it's saying is, and especially you see this in the Sahelian zone up here, in parts of the Sahel, they get almost no rainfall apart from a very sort of small chunk of the year, sort of July, August, June, July, August. And during that period of the year, they get maybe 20 storms, and those 20 storms are it. That's how much rainfall they get in the year. So predicting those storms is really, really important, not just from a seasonal forecasting perspective, but also because those storms are have high impacts when they do fall. And then you'll see that actually, maybe surprisingly, other parts of Africa do receive, although they receive a lot of rainfall, they also have a lot of light rainfall. So this isn't saying that they don't get heavy rainfall. They do get heavy rainfall, but they also get a lot of light rainfall as well. So maybe Africa is wetter than people sometimes think. Okay, so the diurnal cycle of convection is also a really, really important factor in the tropics in general. And over the land, you can see here, so this is just looking at the diurnal cycle of cloud for July, August, September. 0Z, 03, 06 UTC, so 6 in the morning, 9 in the morning, 12, 15, 18, 21. I mean, this is very close to the meridian, so you can see that actually this is roughly the same as local time. It's slightly offset from local time, but it's mainly the same. And what you're seeing here is that if we started at 6 in the morning, you have kind of not so much convection, and it sort of becomes a minimum around 9 to 12. And then as the day builds, the clouds get bigger. They get much, much larger. There's more kind of energy in them. And you get this peak in rainfall and convection around 1821 and 0. Now, the Met Office actually has a network that's a global network of lightning. So we have lightning detecting equipment in Europe, but that lightning detecting equipment can actually detect lightning strikes all over this side of the hemisphere. And so we can detect lightning even in Africa as well. So these plots are taken from the lightning strikes that we've been detected in Europe, but we detect them in Africa. So the equipment stays in Europe, but we can detect them in other places. And you can see the same thing that we show from the satellite pictures. And this is showing that you have a minimum in lightning activity in kind of like the early part of the day, so in the morning. And then the lightning activity builds 15, 18, 21, and then sort of starts dying out again overnight. So you have this kind of building of the tropical storms during the daytime, and then they kind of reach a maximum in the evenings, and then overnight they start dying down again. But even from this, you can see that you can actually have convection at any time of day. So it's not to say that you never get a storm at 9 o'clock in the morning, it's just less likely. Okay, so now let's have a look at the seasonality and how the rain belt, or this rain, changes throughout the seasons. We'll start in January. So in January, the sun is maximum in the southern hemisphere, and so it's further down south. And so at this time of year, you have the Intertropical Convergence zone, which is our kind of big tropical band of maximum convergence on a large scale. So focused over the southern hemisphere. The southern hemisphere intertropical convergence zones are actually really interesting. We could go on and talk about that, but they tend to be diagonally kind of orientated. They go from sort of the northwest down to the southeast. And so you can see that here as well, where the maximum band of rainfall is kind of orientated from Central Africa over to Madagascar and downwards, and it keeps going down as well. In South Africa is a very interesting country from a weather perspective, because they have influences from extratropical storms, as well as influences from the tropics as well. So they have lots of kind of tropical weather and lots of convection. And like I say, this is Lesotho. So in the winter seasons, Lesotho can it's very, very high up, so it can experience snow as well. So going through from January now, as I'm gonna, there's quite sort of a quick animation. It's gonna go through the seasons, and I'll have a chance to kind of look at them individually. But what you're going to see is that this band of rainfall starts moving northwards. The beautiful thing about Africa is it has this lovely seasonality where it does not go the same path northwards as it goes southwards. So the Intertropical Convergence zone, when it's going northwards over the springtime, goes a different route that it goes in the autumn time. So here we are. This is January, February, moving into March, April, May, and you can see that in that animation, you saw the sort of rain band moving northwards. And now by May, what's happened is that you have the rain band focused over here in the Gulf of Guinea. And then most of the rain is actually offshore. So it's happening in this kind of band here. And this is when we're getting a period where there's a kind of the equinox moving northwards, sun's moving northwards. The Intertropical Convergence zone starts moving into the northern hemisphere. If you were to look at a global picture, it starts becoming what you would see in a geography textbook, a really nice, beautiful, long linear feature that kind of moves around the globe. It gets broken up a little bit more over here, and that's due to sea surface temperatures over in the Indian Ocean. When we go from May into June, July, August, there's the West African monsoon, and then the West African monsoons retreats into October. And I sort of showed the arrow, but you kind of have this opposite way that it starts retreating downwards. So instead of kind of coming back the way it came, it starts coming back much more inland, the monsoon. And then going down from October down to November, December, of course, ending up where it began, sort of in that diagonal line across Madagascar. So just to look at that again, you can see that in these images. It's the same thing, but just think, so January, February, March, April, May, moving over the Gulf of Guinea, June, July, August. This is the time of the West African monsoon. I'm going to talk about that in a second. September, October, November. And you can see that difference between kind of November time and April time, or March time. It's quite different. So in April time, it's much more focused over the ocean. And then December, it retreats much more back down over to Southern Africa. Now, the reason why there's this asymmetry in the seasons is down to the asymmetry in the sea surface temperatures. So at the beginning of the year, you get the formation of a warm tongue that starts forming along the Gulf of Guinea. And it's these warm sea surface temperatures which encourage the intertropical convergence zone to be maximum over the ocean compared to the land. In June, July, August, you have the formation of the West African monsoon. And I'm going to show you the process of the West African monsoon in a second. And that's when you start getting the development of cold tongue in June, July, August. But the consequence of that is the ocean is quite slow to react. It reacts very slowly in its temperatures. And that means that September, October, you have much cooler sea surface temperatures than you do in the equivalent time of year in the springtime. So it means that most of convection is then pushed over the land in terms of the balance. So let's talk about the West African monsoon. At the beginning of the season, in springtime, you have the sun is at a maximum over the Guinea coast. This is us kind of looking into West Africa as if we're standing in the Atlantic Ocean looking into West Africa. So we have lots of convection happening at the Guinea coast and some of it over the ocean as well, near the equator. But as the sun moves north, so this is now getting into sort of June time, so when you're having maximum sun, the Sahara starts getting very, very hot, even at night. And so you have this thing called the Saharan Heat Low, because you have so much heat at the surface, the air is rising very, very rapidly, lots and lots of dry convection. And what happens then is at some point, that heat low gets so powerful, you have this very, very like big mass upward movement of air. And you start having a large scale pressure gradient between the kind of northern part of Africa and the southern coast. At the same time, it's basically a little bit chicken and egg, but it starts encouraging a cold tongue to form along the equator. And then you are kind of reinforcing that beautiful large scale pressure gradient. Well, what this does is a pressure gradient. The air moves on large scale from the cold to the warm, and you have a reverse of what you would normally get in the northern hemisphere, where it's actually cooler in the south, warmer in the north. I mean, this is great from a sort of system perspective. You get very few of these things happening. This is what the monsoon is. It's very similar in India as well, slightly different in terms of geography. So you have this large scale kind of circulation that's going around, and what that means is you're pushing the moisture, pushing the storms northwards into the Sahelian zone. And the Sahel zone, if you visit the Sahel, so if you visit Mali in kind of April, May time, it is the desert. It looks like Sahara Desert. It's completely dry, sand, everything. 2 or 3 months later, it looks like Teletubby land. It's a golf course. It is absolutely green. The grass grows so quickly there because it receives its rainfall, and all of the vegetation is adapted to grow very rapidly. Okay, so I think I've said that. So, but in reality, that's the kind of idealized version. In reality, the monsoon inflow is slightly more complex than I've demonstrated in my figure. You get some monsoon inflow from the south, but actually a lot of it is from the southwest, and you can get some westerlies as well. It's kind of this big inundation of moisture into the Sahel region. And what happens is, because of the thermal wind balance, because it is it's the wrong way around, if you like, from a vorticity perspective, you get the formation of the African easterly jet, and any undulations on this jet become baroclinically unstable, and they're barotropically unstable and baroclinically unstable. And this means that you get the formation of African easterly waves, these like positive vorticities that are stuck in the jet, and they move along the jet. So you have African easterly waves that move towards the west, and they have thunderstorms embedded in them. And it's these African easterly waves that often act as precursors for tropical cyclones in the Atlantic Ocean, which is why there's a huge interest in African easterly waves. There's been a lot of literature published on them. So I love African easterly waves. I can talk about them for years. So if anybody wants to know any more about them, then let me know at the end. Okay, and then I just wanted to say that very briefly about low-level westerlies in Central Africa. So Central Africa is kind of, you know, if I have 10 years, I'd love to do a field campaign one day in DRC, in the Democratic Republic of Congo. It's very little understanding about what happens in this region. But as you can see, that's when the monsoon is, when the IGC is over, the main kind of rain band is much more pulled inland rather than being located over the sea, because there's still kind of cool sea surface temperatures over the sea. So Cameroon and DRC are sort of receive much more larger systems, and this is one of the most lightning-rich areas on the planet, if not the most lightning-rich area of the planet. We know that because we can look at the lightning remotely rather than being in situ. And it's basically driven by, again, the same sort of thing, but it's almost a self-contained system, because you get this heating that's formed within the convection, and the heating helps drive a local pressure gradient. And so again, you have a kind of circulation, but it's almost driven by its own convection. I'm just going to say one thing about understanding the large scale. I've lost what time it is, actually. I don't know. I shouldn't take my watch off, but quite often when we're doing weather forecasting, and I'm going to talk about NWP now, the place where we start when we talk about the tropics, because tropical weather forecasting, I'm not giving anything away here, it is way harder than weather forecasting in England. We start on the large scale because it's much easier to understand what's happening. There's synoptic weather systems in the tropics, but they're much weaker. So here is actually a picture that is taken from a tropical analysis that is done every day by the Met Office, the Global Guidance Unit. So we look worldwide to see what the kind of large scale tropical waves are doing. So things such as the Madden-Julian oscillation, or Rossby waves, or the African waves are marked on here as well. And you can start seeing kind of patterns in how the large scale dynamical features are matching up with convection. Not always perfectly, but it's kind of a good place to start. So it's kind of starting with the broad brush peak feature and then moving down to kind of the country level. So let's move on to numerical weather prediction. I'm going to talk about different types of numerical weather prediction, and the things that I'm going to sort of really talk about and why they're important is the difference between global models and regional models. So to really talk about that, we're going to think a little bit about parameterization. If you've never come across the word parameterization before, what it really means is a way that weather models, or the numerical weather prediction models, can represent processes that are happening on scales that are much smaller than the grid boxes that we use in our NWP models. So in this case here, this is Lake Victoria in East Africa. The grid boxes that we might have for our NWP model are much bigger than many of the processes that actually do occur in the atmosphere. So we might have something like clouds, we might have some mountains and some flow over the mountains, and we might have some kind of complex sort of flow around the lake. We've got coastal boundaries and stuff. But you, in your NWP model, have only got a grid box that big, and within that grid box, you've got to represent everything that's happening that's complicated in that grid box. So we only get one number for the whole grid box. So let's think of an example of a cloud. Let's say we've got a clouds that, obviously those aren't real clouds, but imagine we've got a group of clouds that look something like that. How might we represent them in terms of numbers on the grid box scale? Well, you probably get something that looks more like that. It's more blocky. So the grid boxes are bigger than many of the processes that occur in the atmosphere. So we have to represent those processes using parameterization. That's what we call it. And this is basically where one number is representing the grid box. So what do we parameterize in our NWP models? There's a few things that we parameterize. First one is orography. So orography is mountains, and also the effect of things like the coastlines and everything effectively that's on the map. Nicely, that doesn't move too much, so that's quite good. But clouds and microphysics is more complicated. So the transport of moisture in phase changes within a column. Convection, which I'm going to talk about a little bit more detail because it's very important for Africa. But also the boundary layer and radiation as well. So that's radiative transfer in terms of like the surface energy balance. So let's talk about convection parameterization. This is kind of a typical convective system in the real world. What might it have? Well, it's generally got an updraft. It's got a downdraft where cool, dry air is being pushed out of the storm. And then the downdraft will have a kind of, it will hit the ground and it starts fanning out. It'll also have some entrainment of dry air into the storm as well. And the entrainment of dry air generally kills the storm in the long term. But it's also got some detrainment of moist air. So it's also interacting with its environment, especially at the anvil level. So how do we represent that in convection parameterization? Well, we simplify it right down to basically 4 numbers. One is a mass flux, so this represents the total mass in the column, so that's going upwards and downwards, so it's a down plus up, if you like, so it all represents like M. We've also got detrainment and entrainment, and you can kind of mess around with these and say, like, oh, I think there's going to be more entrainment or less entrainment, but you have to do it for the whole model that you're running. And as well as that, outside of storms, so when you don't have a storm, you've also got substance, so you've got general sinking of air. So air is rising in storms and sinking outside of storms. So when the grid spacing is big, you'll get this kind of, you'll basically got this calculation happening in every grid box. Now, if you have clouds in every grid box, we're looking at a cross section now, what that means is that you basically have a number per grid box that you're calculating from all of those parameters. If you have more grid boxes, you have a slightly better representation of the clouds that you have. So kind of you just basically representing it. It's very similar to a photograph. If you've got more pixels in your camera, then you've got a better photograph. When the grid spacing is very small, something great happens, which means we can switch the parameterization off completely and we can represent the processes explicitly. Now in the UK, convection, if you have a look at an average storm, how big is it in the UK? Maybe 200 meters, something like that. You know, if you look out the window, you can normally see it. You can see it from side to side, a storm. In Africa, the storms look like the apocalypse when they're coming to you. They are huge, end to end, the size of Wales. You know, they are massive, massive storms. And so actually, if your grid spacing gets down to about 4 kilometers, sounds a lot here, you would have a storm that's much smaller than 4 kilometers in the UK. But in Africa, actually, that starts coming to the point where, you know, 4 kilometers could be that much of a storm. It could be a very, very small amount of the storm. So you can have multiple grid boxes that are representing one single storm. And that means that you can have one grid box that's representing like the updraft, one that's representing the downdraft. You're much more likely to be able to successfully represent the processes within the storm. I just wanted to pause a minute and talk about the NWP models that Africa has access to. So the national weather services in Africa are very different. They all have different flavors. Some of them are very, very developed and look much like this. Others are very basic and they look much more simple and they might have only about sort of 10 staff. So it depends which one you go to. But all of them have access through the WMO to a lot of international models that are produced by the global producing centres. So the global producing centres that produce models that are available to Africans through the WMO are the ECMWF, so European Centre, based in Reading, the Met Office, based in Exeter, and NCEP in the USA. And we provide our model information to Africa free of charge in kind of exchange and for the observations that they provide to the WMO. So it's kind of a voluntary cooperation program. So we cooperate, everybody cooperates together. But as well as that, many of the national Met services in Africa run their own versions of WRF and Cosmo. Additionally, the South African Weather Service is actually a UN partner. So they run the same model that the Met Office runs, but they run it just over Southern Africa. They have it for their own region. But one of the things that Met Office also does, we have a global model, which is parameterized, but we have, I think, this very special model, which is the Tropical Africa model, which we started running in 2019, which has explicit convection. So it's a really wonderful type of convection that's much more realistic and looks much more like a satellite image. However, a note of caution on high resolution. One of the things that we see when we look at higher resolution models is they look much more like satellite images, they look much more realistic, but they're still a model. And what we find is that we can't be so specific and say that storm is absolutely going to happen in that location. in the same thing we have in the UK. If you have a look at the weather forecast for today, and you're looking at, I looked at the telly this morning, the storms that they predicted that were coming up aren't exactly in the right location. They might be quite sort of similar, but not quite exactly in the right location. You wouldn't be able to pinpoint the town. You might be able to pinpoint the sort of 50-kilometre box that it occurred to. So the smaller the grid box, it looks real, but we have to be really careful about how we interpret it. So if we were to just say verboten, it's going to rain at village C, it's not going to rain at B, and it's going to rain at A. Village C would think it was a terrible forecast, it was a false alarm. Village B would think, actually, you told me it wasn't going to rain, and it rained. That's a miss. Village A goes, oh, what a wonderful forecast. So, what we probably do is, instead of saying very specifically at point locations it's going to happen, we say across that whole region, there'll be rain showers, which is why sometimes weather forecasts sound a lot more vague than perhaps they could do, because actually, if you look at point locations, you're not often correct. Okay, I'm going to talk a little bit about data assimilation. Nobody's leaving, so that's always a good sign. But look, this is an important subject because data assimilation is about how we put the observations into the model analysis. And having a good model analysis is like the #1 thing that gives you skill for your forecast. So, in the 50 years of forecasting that we've done, when data assimilation really got going in the 1990s, you saw this massive leap in skill in forecasting. And it's all because of data assimilation. So forecasts are initiated from a model analysis, but you need data everywhere on your grid to be able to forecast everywhere on your grid. Of course, you don't have data everywhere on your grid because observations don't exist everywhere. So imagine we had 3 observations across this whole domain. Like imagine this is West Africa and we only had 3 observations. Those are temperature observations or something. It doesn't really matter what they are. We also have a model background that was from the previous forecast. So we had yesterday's forecast valid for today, but these observations don't quite fit with the most recent forecast. So we alter the model reality that best fits the observations, and that creates the model analysis. It's noted that not all observations can be perfectly fitted to the analysis. So sometimes you get an observation that doesn't quite sit exactly with the model analysis, and that can be confusing. But the reason is that it has to be some compromise. Otherwise, you can end up pulling the model too far and you get some kind of problems with the numerics. The more observations we have, the more we can constrain and have confidence in analysis, and the more reliable the analysis is, and that improves the forecast. I'd also say some observation types have more impact than others. So let's take the example where we might have a few more observations. Let's say we've got all of these observations. We're now getting a slightly better fit to our model, and we can be more confident of our model analysis, and that generally means you get a better forecast. If the model has really high resolution, but there are not very many observations, the crazy thing is that data assimilation can actually be worse than just using the previous day's forecast. So in this example, imagine this was the previous day's forecast, and we really were forcing it to focus on those 2 observations. And in the previous one, we know that this observation was kind of ignored because there was other observations to be able to rely on. But if we were like, no, you have to focus on that observation, you might end up with a field that looks completely different. In other words, if you don't have very many observations and you've got high resolution, you can't really use data assimilation. So then we have a problem. What do we do? Well, what we actually do in Africa, where there's not very many observations, and actually everywhere the Met Office does regional modelling, apart from the UK, we don't use data assimilation in our high resolution models. We use the global models analysis and we downscale that. So we effectively make it much finer resolution in the analysis. And then we run the regional model from that high resolution version of the global model analysis. So the global model's still got data assimilation in it. So all those lovely observations that are being collected by Africa and shared on the international network are still going into the regional model. They're just going in through the global model. So there's a bit of kind of 2-step to it as well. So the high resolution regional model is initialized from a low resolution global model. What that means though, the compromise we have, even though this is a much better analysis for things like temperature, winds, the compromise we have is that convection or rainfall is taken also from the global model. And the global model, because it's parameterized, does not have as good convection as the regional model. So what this means is in the first 18 hours of the regional model, the convection doesn't look very good. It looks more like a global model. And that means that we don't get the benefit that we would normally expect from an explicit model. So what we normally say is that intuitively, if you're forecasting for Rwanda or Uganda, say, and you came in the morning, 6 a.m., 7 a.m. in the morning to do a forecast for the day, you're better off looking at yesterday's forecast to see what was going to happen this afternoon than you are looking at this morning's forecast, because the spin up of the model takes time. So there's an example here. So this is the observations over Lake Victoria. You can see there's a storm over Lake Victoria on this particular day. And actually, the T plus 27 hours, so this is a 27-hour forecast, these are all valid at the same time, have the storm in. So if you looked at the forecast that was out long, it looks actually really good. But going closer to the event, the T plus 15 doesn't have it in, suddenly it disappears because it's much closer to the event, it's much more affected by the global model. And the T plus 3 has got almost nothing in it. It's not there at all. So just kind of looking at the differences between these two models, this is the 10-kilometre global model, and this is the 4-kilometre regional model for a particular day. So this is the parameterized, and this is the explicit convection. So the parameterized convection tends to be quite good at the large-scale picture because it's got large-scale dynamics in it, assimilated from the global observations. But problems are there's lots of widespread rain. It's not very detailed. The rain hugs the coast. It looks awful. That's a problem with parameterization. Luckily, in more recent versions, that's getting slightly better. This is taken from about a year ago. It tends to rain too early in the day and not enough in the evening time, so the Dyno cycle is not quite right. Remember we said that was important. The reason for that, again, is the parameterization. There's no storm-like features, and it's unrealistic. Whereas the regional model has more realistic thunderstorms and rain happens at the right time of day. However, sometimes the rain rates can be too high and there's too much detail. How am I doing for time? I can't see.
Oh, yeah, 10 minutes.
10 minutes, oh my God, okay. So I wanted to get on to kind of this last section of slides, challenges for national weather services in Africa. So we talked a little bit about models. How do they do weather forecasting? Everybody does weather forecasting differently, so I'm not going to try and claim that I've been to every national Met Service because I haven't. But for the ones that I've been to, actually quite often they go back to kind of the fundamentals of weather forecasting and look at synoptic charts. This is in Malawi, so it's slightly easier for them to use synoptic charts because they're closer to the extratropics. So it's a little bit more relevant for them where the high and the lows are. I also wanted to show the challenges can also be the personnel. So in this Met Service, one of the challenges they have, they didn't have so many people who were available for forecasting. So this guy was very busy. He was not just doing the forecasting, he was also updating the website. And he was also writing all of the scripts for the TV and then presenting the TV as well. So he was a very busy guy, he was a great person. There's also challenges with observations. So this is taken from Rwanda. You can see here, this is an automatic weather station donated very kindly by a donor NGO. Can we see any problems with this automatic weather station? Yeah, absolutely. So the people who installed it, as kind as they were, and as well-meaning as they were, they didn't actually know anything about meteorology. And they installed the automatic weather station in a way that was completely useless. It was too close to trees, and it wasn't in line with what the WMO recommends for weather stations. So actually it ended up being just an expensive piece of kit in the field. And not only that, it caused more problems because then the Rwandan National Met Service had to come out and try to move it and maintain it. So we had to do basically double the work that it would have done in the first place. This is another automatic weather station, this time in the middle of the desert. Maybe you see the problem with this one. A bit harder to see this one. So the thing that was funny about this was in the middle of the Malali, this is in Mali. So the whole region was actually mostly this red sand. This was looking more towards the grassland, but out the other way it was grass. This is looking at radiation. Because there was so little moisture in that part of Mali, what would happen is the moisture would gather on the instrument and it would drip down onto the sand. And like I say, the vegetation there is adapted to basically grow as soon as it gets any moisture. So below the one place where you're looking at radiation, you have this very unrepresentative patch of grass that has grown just below where it's dripping. So it starts becoming very unrepresentative because this is our only number that we've got for the whole region. And actually most of the region was sand and desert. And so it kind of looks actually like the vegetation is starting much earlier in the year than it is because of this moisture effect. And then archiving can be a problem as well. So you know, sometimes they have these wonderful paper records that go back to the 1800s, but it's hot and it's wet and it's damp a lot of the time. And sometimes a lot of the archives don't necessarily have air conditioning and things like that. So keeping good archives is a real challenge as well for some places. Finishing on challenges of technology. So I work in technology now, and I kind of moved into technology because I could see that actually there's a lot of things that we need to solve with technology. IT infrastructure, security, and digital services might not be sexy, but they help something function. You probably take it for granted that whatever workplace you work at, if you've got security and you don't have somebody hacking your accounts, there's somebody in the background that has made that happen. So the infrastructure teams, the security teams, and the digital services teams that keep websites running are really, really important people, and they're really expensive people as well. And it's really difficult if you have those skills. They're often in high demand, especially in developing countries, and it's hard to persuade people to work in national med services. Here you can see a picture. It's the same guy from earlier. This is him updating the website. They had equipment for viewing the model information on a separate Linux machine, and they had to call out numbers to a separate machine to be able to input them into the website. So a lot of the technology is just not sort of linked up. To be honest with you, some of this stuff is not quite like this, but there's even some of this stuff that still happens even in the Met Office. So just sometimes technology is one of those enablers that really should be a lot easier and a lot clearer than it can be. Finally, I want to talk about plotting, coding, and visualizations, one of my big bears. We have all this beautiful NWP data, and we're not necessarily very good at visualizing it. So we have big problems with visualization, and it's really upsetting because if the models are good, but we're not actually seeing what they're able to produce, then it's completely pointless running models. These two pictures here, I just put them here to remind me, these were actually produced using Python, and this one was produced using a program called GRADS. Now, GRADS is a program that started over in a university in in America. It is now unsupported completely, so there's no grant supporting it whatsoever. It is by far the coding language that I see used most in developing countries, both in Africa and Southeast Asia. I think it's wonderful. I could teach somebody to use GRADS after this. It's a really, really simple coding language, and you can get plots really quickly. So I'm a big advocate of it. Python's wonderful as well, but it's just a little bit more complicated, and it does take some kind of perhaps coding pre-knowledge. I wanted to finish with some hope for the future. So these are kind of technology frontiers that I feel really hopeful about for Africa especially, but really for anywhere in the World Meteorological community. The first one is on prediction. So I think that we're kind of at a nexus with prediction. In the 1950s and 1960s, compute power started getting powerful enough that we could start playing with the idea of numerical weather prediction. Now we take that for granted that everybody does it, and the Met Office has got a huge amount of people dedicated to improving our NWP. I think we're at the kind of next nexus where people are still treating machine learning and data science and artificial intelligence as a bit of a novelty. But really, I think it's probably the future. Mixing artificial intelligence, machine learning, integrating it with NWP is going to be the next kind of frontier of where weather modelling is going to go, not just for Africa, but for everywhere. But for Africa, that's really good news, because actually NWP isn't great. And so we do need to try and move forward and think about other ways that we might be able to complement what's already there. There's even people working within University of Leeds on machine learning in the tropics. So that's great. But this is really at university stage at the moment. The next one is on data and compute. So one thing that has kind of been a bit of a barrier at the moment is that most of the national Met services in Africa have not been able to run high performance computing. It's very expensive to do so. We have like 4 warehouses down in Exeter that are running our supercomputers. They're huge, they're very expensive to maintain. Met Office is getting rid of its supercomputer. We will no longer be running a supercomputer in Exeter as of in the year's time. Our supercomputer is going to be run instead by Microsoft. We are paying Microsoft to run a supercomputer for us. And the reason that the Met Office chose to do that is because we have no interest in being supercomputer experts. It is a means to an end. So if we can buy that as a commodity and somebody else wants to run it, great, we're happy to do that. We don't really want to, we can't actually afford to pay people to do supercomputers, because people who run supercomputers are very expensive people. They're hard to recruit. They work for the government, but they will work for Microsoft. So we are moving towards cloud computing and working on HPC as a platform. And the great thing about that is that all of our data will also start becoming more cloud and platform friendly. And the nice thing about that is that it's a leveler. There's no reason why other people in other national Met services can't access our data. They should do in the future. It should be the World Meteorological Organization is really well set up to be this kind of, I think, a really great bastion for data sharing worldwide. And it's beneficial for everybody. There's no reason why we shouldn't share weather information. So we'll have some global APIs. And the other thing is things like Jupyter Notebook. So again, even if you're doing analysis on weather information, it can be quite compute hungry. But if you don't have to have now a supercomputer or even a very powerful machine underneath your desk. You just connect to the cloud and the cloud will do the work for you. Like it will be a supercomputer in like London or Washington or somewhere like that. So that's really brilliant. Finally is communication. This is where I really think sometimes the national Met services in Africa are more forward thinking than we are in Europe. I always think of them as like speedboats. They're really on top of things. With the GCRF African Swift project, there was a project between lots of national Met services, so Kenya, Senegal, Ghana, and Nigeria, where they looked at kind of co-producing and talking about how to communicate weather forecasts with the public. So they were talking directly to customers about how they would like their weather forecasts built. Even in this room, Michael Baidu set up a WhatsApp group in Ghana to share weather information. This is far ahead of where the Met Office is, the UK Met Office, right? And so these kind of small scale initiatives that happen in Africa are often kind of far ahead of where we are in the UK, because we move very slowly and very officially, whereas actually they just get things done. And so I think like things like co-development, app-based communication, things that are much more locally targeted, and because a lot of these countries are quite small, they can be more locally targeted, integrated into languages is really, really positive and is quite very, very forward thinking. I really, really want visualization to get better. I think it's still a bit of a black hole at the moment, and that's kind of still where I think there needs to be a lot of work done. So just to summarize the talk, forecasting Africa is extremely challenging due to the type of weather, the access to NWP, and the limited observations, limited technology. But I do think there's hope on all of these fronts, maybe apart from the weather. The Met Office has this voluntary contribution programme, and if you want to know more about the programme, it's a terribly long, but you can find it through links on our website. If you look for our international work, it actually says, and there's some nice videos on there as well, from the things that the Met Office pay for. So we pay for observations, for training, and also for TV weather studios in all of the national Met services in Africa, as well as share our data as well. And that's it. So I'll happy to take any questions.
Well, great. Thanks so much, Caroline, for the great talk. I've learned so much, and then I'm sure we have we had a lot of things to absorb within a short time. So there's certainly a lot of clarification that we need to get within this period. And thanks so much for everything. I didn't know that creating a WhatsApp group for sharing some of the station data is an outstanding. Okay. If you have any question in the room, feel free to put up your hand, and then if you're online, just put it in the chat, and then Ben's going to read it out for us. Yeah, cool.
Thank you. Do you use satellite data as well?
Yes, yes. So remotely sensed data is really, really important in data sparse regions where observations are poor. Satellite data is really great for top of atmosphere brightness temperatures. It's not very good for the surface. And of course, ironically, quite often what you want to see most is the surface when there's a storm above it. So if the storm's there, it's blocking what's happening at the surface. We calculate rainfall from a satellite rainfall product often. So that's worldwide in the tropics. It's not just a problem in Africa. We just don't have as many observations. And so a lot of the kind of tropical rainfall is estimated from satellite.
Thank you.
Yeah.
Just wondering, when you talk about the progression of the monsoon in West Africa, when it's sort of heading northwards and you get this big cold water upwelling, does that have anything to do with some of the droughts that may be happening more towards the coast in West Africa?
Yes. So it's not droughts, but one thing I didn't mention is when the rainfall moves northwards, so it moves kind of into the Sahelian region, Ghana and the kind of coastal regions, especially the lower part of Ghana, receive this kind of little dry season, they call it. It's called the little dry season as well.
Yeah,
I feel like I'm
yeah.
Michael's the forecaster in Ghana, but it's called the little dry season along the coast of Guinea. So it's actually, you get this kind of period where there's few bits of rainfall. However, I mean, I didn't talk about it. There's a few little bits of rainfall there, so it's not like it's dry completely, but it's just not the maximum time of rainfall because most of the rainfall has kind of shifted. That very heavy rainfall has shifted northwards to the Sahel region. Yeah.
Why should you not install automatic stations in trees?
Because it's not representative of the wind in the region, in the area. So the WMO standard is that you tend to have quite a large enclosure that is generally free from ground clutter around it. Because, for example, if you can imagine, and actually even the Met Office weather station is not put in the best location, there's never a perfect, I mean, perfect is in the middle of a field, but what you wouldn't want is you wouldn't want a weather station that's the only place that's representing the whole of Leeds, for example, and it was like down there, right? Because it would be near the buildings, and so you wouldn't get a good you want kind of a number that is representative of as much of the area as possible, and that's why it's kind of slightly better if you put it where there's no obstructions nearby, so that the wind is relatively unobscured by local influences. So the trees are making the winds much lighter than they would be if it was in a more kind of open area.
Yeah, and actually in some places in Africa, you don't have a dense network of observation stations. So if one single station is supposed to represent the weather of a whole big city, then it really has to be in a very good place to represent. Yeah.
Really interesting talk. Thank you. Just wondered to what extent you link with fisheries, because most of my research has been fisheries coastal. And just thinking about the extreme weather or hurricanes, cyclones. I think, fishermen in the UK, they have access to about 10 different apps. But in Africa, especially some of the unsustainable fisheries, don't. I just wondered where the scope is.
I need to repeat the question because I think those online are prompting us that they do not hear the question. So basically, she wants to know what extent we link with fisheries, because she's studying about hurricanes, the initiation of hurricanes and stuff like that, and we need to
Okay, so in answer in terms of fisheries, fisheries are a huge not issue, but there's a lot of, so I had a project, or we had a project, the WMO had a project with the National Met Services around Lake Victoria called Highway, which took place 2018 to 2020, I want to say. And that had been on the cards for a long time. So back in 2012, 2013, we had reports there were up to 5,000 deaths a year on Lake Victoria from fishermen that had gone out. And what tends to happen is that they fish at night time because they use lights to attract the fish, and that's the best way to do fishing. But Lake Victoria has a very strong diurnal cycle, and they also get the most storms at night time. They'd go out in these canoes, and they'd be miles from shore, and then a huge storm comes down, a massive downdraft spreads out, and it doesn't take that many big waves to rock a boat, a small canoe over, and then there's no rescue boats nearby. You know, you're kind of stranded in the middle of the lake. So what the National Met Services has started doing is having, and again, this is where I think they're a lot more agile sometimes than we are in the UK. They have, so in Kenya, for example, they have regional Met services that have direct connections now to the beach management units on Lake Victoria. The beach management units, the people who are kind of almost like the Coast Guard, had specialist training and do workshops with the National Met Services. And through that, they've now started doing boards, kind of, so before the fishermen go out in the evening, they can see what the chances are of storms, and there's warnings and stuff. It's not perfect, and actually one of the limiters is that our weather prediction is not great. So there's still kind of a kind of limit as to how successful they can be, but at least they're now getting forecasts. Again, the ingenuity, very quickly, the National Met Services in Uganda and Kenya set up WhatsApp groups. So there's these large WhatsApp groups of fisher communities where they kind of share the information. So every country is slightly different on how they tackle it. It's never going to be perfect because our weather prediction is not perfect, but I have quite a lot of hope that actually a lot of the African countries I've seen it are a little bit more forward thinking when it comes to actually how can we communicate this. The difficulty and the flip side of that is how do you maintain it? Because you still need somebody then to be texting every night and saying what the storm's doing and stuff. And fitting all of that kind of production, we'd call it, so kind of product production into a schedule, into a daily schedule is quite challenging. It's challenging for any forecasting service, but it's especially challenging if you have all these microservices that you're trying to maintain manually. So it's not a solved problem, but I think that's something that would be interesting to tackle in the future.
So, sorry, go ahead.
No, go on.
You're telling the guys on Big Lake Victoria, don't go tonight, it's going to rain. Did they take any notice?
Yeah.
83 off, sell off, living, etc. Do they take any notice?
Sometimes, yes.
Yeah.
So the answer is not always. It depends how the storm warning is. We've had feedback from the pilot studies that we did as part of that project that there were, well, the feedback that we got, it's difficult because people are very polite, so they only say like positive things sometimes rather than critical things. But the feedback that we got is that the fisher communities felt that it made a big difference.
Okay.
Yeah. But you are right, that is also one of the issues. And
Yeah.
it's even the issue in the UK. You can issue a red warning, but you can't stop people getting in the car and going on the M20 when it's snowing. You know. Sorry.
Okay, we'll take Helene's question and then we have a
I'm
question
not,
online.
I'm not asking a question, but I'm just complimenting on what she was asking about the Lake Victoria. I'm from Tanzania.
Yes, I know.
Yeah.
Yeah. I was very timid about saying anything about Tanzania because it's like,
Yeah,
Helen's going to correct me.
No, you're free to say. Okay. Yeah. I really appreciate what UK Met has done in Tanzania, and I know we have been communicating in several times. It's true, it's very challenging focusing in Africa, and we are grateful for all the development in terms of technology and WP, but also on user engagement. So the user engagement has been a very good tool for us to improve forecasting and delivering services to many users. For example, the question she was asking about the fisher community, it started way before the high impact weather. It started with the mobile weather alert.
Yes, it did. Yeah, in 2012. Yeah.
Yeah, a little bit. Yeah, in 2012. So from those engagements is where now we came up with how we can effectively communicate with the users. Yeah. And also we changed even in Tanzania the way we were issuing our weather forecast, because it was 24 hours. And within 24 hours, when you talk to the fisher communities, they want like 3-hourly forecasts to be able to,
Because if you're just issuing a forecast once a day and you say there's a chance of storms today,
I was just
thank you. I mean, I think it's really hard to tell how effective things have been, but I was working in Lake Victoria since 2012 as well, so I was involved in the early part of this mobile weather alert. But it's hard because you see these, you have individual interactions, but you don't know how far it spreads. So it's really nice to hear that it is something that has made a difference. Thank you.
All right, so there's one question online that I want to read from William Taylor. He says that, how does the observed data density in Africa compare with, for example, Europe or UK? So what are the average distances between observing stations?
Okay, so so everybody said that. Yes, they are. So this is where it's tricky, because when I first started working in African meteorology, I was, we should put loads more observations in Africa, there's not enough, blah, 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 blah. And then as I started working in international development, I saw the problem that I showed earlier, where there were these well-meaning NGOs who'd spent huge amounts of money on kit, but it hadn't been properly installed. And then it often, they install the station, the weather station, ta-da! But then it costs money to communicate the data back to the weather service. So you have to have a mobile phone SIM card, and you have to pay for the data to come back. So you're paying for data to be communicated back to the weather service. So actually, you're like, oh, here's a present, but it's going to cost you £100 a year. It starts becoming a bit more of a burden on the weather services. So quite often, although well-intentioned, a lot of the old projects that have installed weather stations have not then also paid for their upkeep. And so they've just installed the kit and then kind of left it. And the weather services, which are often very highly pressured in terms of the amount of people they've got and the amount of money they've got, because they don't have very much money from their governments, can't maintain those weather stations. And so you end up with these kind of deteriorating weather stations. So this, in terms of answering that question, Africa has a lot of weather stations. There are really, really a lot. But how many of them are functioning and reporting to the World Communication Network? Very few of them. So in terms of the distance between the weather stations, a lot of them are in populated locations, but not so many of them are actually being reported onto the World Network. It's why I can only say again and reiterate the acknowledgement at the beginning, the national weather services that do put their observations onto the World Network, they put a lot of effort into doing that. It costs them money, and it is massively appreciated, and it hugely impacts and improves the analysis that we have on our global models, which then feeds into their weather forecasting models as well. So it helps everybody, but it's not an easy task.
Cool. One more round of applause for Caroline for this excellent talk.
Thank you.
So thanks so much for the great talk. We've learned a lot, and I just wanted you to know that the talk and today's talk, and as well as for the previous ones, are recorded. If you want to listen to it again and again, visit our the Almet Yorkshire YouTube page, and you're going to find the talks uploaded there. And information about the next talk will be sent to you in the course of time. So keep looking forward to it. Keep an eye on our webpage, and you'll be informed. Thanks so much for being here with us, and then see you same time next month.
Thank you.